This video is about generation of carbanion and its reaction. In this topic, you should know two basic points. They are: base can abstract acidic proton to give anionic species. The second point is anions are nucleophile. The first point, I use the word base and acidic proton. You should have a clear idea about base and the concept of acidic proton. First, let us go for base. Base is a substance which can abstract a proton. We can classify the bases like this: hydroxide, carbonate and bicarbonate. They are referred as inorganic bases. I can go for some metal here like KOH, NaOH, sodium carbonate, potassium carbonate, cesium carbonate, sodium bicarbonate. It goes like this. We also have metal hydride like sodium hydride, calcium hydride. They also can act as base and they are inorganic again. The next category is carbanion or metal amide or alkoxide. C minus, N minus, O minus. So they also can act as base. For example, I can go for methyl lithium or butyl lithium, sodamide, here sodium methoxide. These are organic bases. Also, we have nitrogen containing compounds like pyridine, triethylamine, diisopropyl amine, diisopropyl ethyl amine, DBU, DAPCO, and it goes like this. They are amine based bases. So we have these four types of bases. The first two are inorganic, the second two are organic. In general, when the reaction is carried out in aprotic solvent, we go for these three bases. In polar aprotic solvent like THF, these salts will be insoluble. Because of that, the reaction will not be favored. The second one, acidic proton. Consider a hydrogen which is attached with halogen. Halogen is more electronegative. Because of that, it will dissociate to give H plus and X minus. So this is acid. HCl, it is acid. HCl will readily dissociate to give H plus. Suppose if I go for carboxylic acid, this also will dissociate to some extent to give H plus. But the dissociation will not be complete. So this hydrogen is acidic. Suppose if I go for methanol or alcohol. In the previous case, hydrogen is attached with oxygen. In this case also it is attached with oxygen. But compared to this, this is less acidic. It will not dissociate to give H plus, but when I treat this with sodium hydroxide, I will get this one. So I can get minus charge like this. This is nothing but sodium methoxide. What is the reason? In both the cases, hydrogen is attached with oxygen. But this dissociates readily compared to this. This is more acidic compared to this one. The reason, resonance. The lone pair involves in resonance, because of that del plus on this is more. But in this case only inductive effect. Oxygen is more electronegative, so the electron is pulled towards oxygen. So we have del plus because of inductive effect. In this case there is resonance as well as inductive effect. Similarly, when I go for amine, this hydrogen is acidic, but compared to this is less acidic, because here we have only inductive effect. Compared to oxygen, nitrogen is less electronegative. So because of that, del plus on hydrogen is less. So if you use stronger base like NaH or butyl lithium, you may be able to abstract this hydrogen. Finally, when I go for carbon, this hydrogen is not at all acidic. Even if I add butyl lithium, the strongest base, there won't be any reaction. We will not get the corresponding anion. At the same time, if I attach some electron withdrawing group, because of this electron withdrawing group, the hydrogen will become acidic. It will involve in keto-enol tautomerism. This is the enol form. Since it is attached with oxygen, this will be somewhat more acidic. You can visualize like this also. So, when I add a base like sodium hydroxide, I get the enolate. So, as such, the hydrogen in alkene is not acidic. But when I attach electron withdrawing group, the alpha hydrogen will be acidic. So based on this, I can say the alpha hydrogens in aldehyde, ketone, ester, anhydride, NO2, nitrile, and even amide. Based on this, I can say the alpha hydrogen of these many functional groups are acidic. If you add a base, it is possible to abstract the hydrogen. What we get is the corresponding anion. Here it will be electron withdrawing group. As soon as you see a base on the arrow, you have to think of acidic proton. The base, it has to abstract the acidic proton. So you have to look for the acidic proton. Generally, the alpha hydrogen of these functional groups will be acidic. This is one method of generating carbanion. We have a few more methods to generate carbanion. To bromobenzene, I add magnesium. You may know we get Grignard reagent. Similarly, you can go for methyl bromide also. We get methyl magnesium bromide. They are referred as Grignard reagent. In Grignard reagent, the carbon carries minus charge. Magnesium carries plus charge. Simply, we can say if there is any metal and atom bond, let's go for carbon. The carbon will carry minus charge, metal will carry plus charge. Not only carbon, even you can go for nitrogen and metal, oxygen and metal. There will be minus charge on this atom, there will be plus charge on metal. For example, sodamide or LDA, sodium ethoxide or potassium tetrabutoxide. The next method is lithiation. Let us take iodobenzene. To this, if I add butyl lithium, the base abstracts iodine. If you compare carbon and iodine, the electronegativity of iodine is somewhat less compared to carbon. So the minus charge will attack iodine. As a result, what we get is this one. Here I have carbon and metal. So there is minus on carbon, plus on lithium. This is another method. It is referred as lithiation. Now let us go for the reactions of carbanion. Consider you have a carbanion like this. This minus charge has 2 electrons. This can be used to make bond with electrophile. The minus charge is used to make bond. For example, I go for methyl iodide. This minus charge attacks here. Iodine is the leaving group. What we get is this one. This minus charge is here. In iodomethane, iodine is displaced with the carbanion. Not only this, even you can go for allyl bromide or benzyl bromide. We have so many alkyl halide like this. Second one, the carbanion can attack carbonyl carbon. Here I have del plus on carbonyl carbon. So this can attack carbonyl carbon. When it is attacked, the number of bonds on carbon will become 5. So I move this over oxygen. Since it is more electronegative, it will pull the electron. So what we get is this one. Minus charge is used to make bond here. This bond goes over oxygen. Since oxygen is more electronegative, this bond goes over oxygen. You can try with imine also, or with triple bond N, that is nitride. Next one, carbanion can be added to alpha beta unsaturated system also. In the case of alpha beta unsaturated system, we have resonance and we get plus charge on this carbon. This is alpha beta carbon. Because of inductive effect, we have del plus on this carbon also. So the minus charge can attack this carbon because we have del plus, or it can attack this carbon. So we have 2 possibilities. Here the minus charge has attacked this carbon. If it adds to beta carbon, then we get like this. This is referred as 1,2 addition. This is 1,4 addition. I go for the aromatic analog of alpha beta unsaturated system. You can compare this part with this one. I have made a ring and I have gone for aromatic compound. Because of resonance, I will get plus charge on this carbon, similar to the previous one. But the nucleophile will not attack that much easily. It will attack when I have more electronegative halogens. When I have fluorine here, this will attack. What we get is the intermediate like this. Here fluorine will be there. It is similar to 1,4 addition. I can say it is 1,6 addition. When it comes back, the fluorine will be removed, we get the product. So fluorine is displaced with carbanium. This reaction is referred as aromatic nucleophilic substitution. Now let us go for a few reactions. Phenol is treated with sodium hydride, a base. It has to abstract acidic proton. We have here acidic proton. If I treat with this compound, what will happen? Minus has to displace this. The product will be like this. Suppose if I add benzyl bromide, we get this one. OH has been protected. Similarly, we can go for paramethoxy benzyl chloride. The product, whatever we get, will be here. I have summarized most of the functional groups and the acidic protons present in them. In the case of carbonyl compounds, the alpha hydrogen is acidic. It is mainly because of resonance. The electron withdrawing group makes the alpha hydrogen acidic. Not only with carbonyl compounds, even in the case of nitro compounds, nitrites and sulfone, the alpha hydrogen is acidic because of electron withdrawing group. We have trimethyl sulfonium, sulfoxonium, phosphonium salt also. Here, the alpha hydrogen is acidic. It is not mainly because of resonance, it is because of the plus charge on the sulfur atom or phosphorus atom. Even we have quaternary ammonium salt. When there is N plus or when there is atom with plus charge, the alpha hydrogen will be acidic. Since it carries plus charge, the electron density will move towards sulfur. Because of that, this hydrogen will become more acidic. So the reason for this is inductive effect. Similarly, in the case of silyl compounds and ether and chloroform, the hydrogens are acidic. It is because of inductive effect. In the case of alkyne, the sp hybridized hydrogen is acidic. The reason is hybridization. This carbon is sp hybridized. The hydrogen which is attached with sp hybridized hydrogen will be acidic. When you go for hydrogen that is attached with sp3 carbon, that will be less acidic. Compared to that, hydrogen that is attached to sp2 carbon will be more acidic. Hydrogen that is attached with sp carbon will be highly acidic. So this hydrogen is attached with sp hybridized carbon, so that is acidic. In the case of cyclopentadiene, this hydrogen is acidic. The reason is aromaticity. When I remove the hydrogen, what I get is aromatic compound. So from non-aromatic, I get aromatic compound when I abstract the proton. Aromatic compounds are more stable and non-aromatic compounds are less stable. So non-aromatic compounds tries to become aromatic by losing its proton. So this hydrogen becomes acidic. So mainly these four are the reason for the acidity of hydrogen. Try to apply these concepts for the remaining functional group also. So as soon as you see base on the arrow, you should look for acidic proton. So this chart may help you to find out the acidic proton in a particular functional group or particular molecule.